Okay.
Good morning. This is Mark Richardson, speaking from our office here in Scotts Valley, California, Northern California. It's 9 o'clock in the morning, so welcome to all of you who are going to attend this webinar for the next hour. We are going to record this, and the topic of discussion is going to be the use of our programming, our macro programming in ME Scope, and also the use of our fax capability that is in our console software, which is an extension of ME Scope, a new option, a new series of options that allow us to log data into a much larger database and then look at trend plots and compare what we call snapshots of data that have been logged into the database with known faults in machinery so that we can identify a fault when it occurs in a machine. So here you're looking at the project that I used last month. This is the 7 unbalanced cases. Let me just mention in the starting here that we are going to provide copies of the projects. We're going to look at 2 different ME Scope projects this morning, and also some tech papers, a couple of tech papers that explain what's going on here in ME Scope and in our console software. So let me start by doing that, and we'll look at these papers and remind me, and we will email to each of you copies of the papers and the project. So you can run this if you're an ME Scope user and you own a copy of ME Scope. All of this software will work on your computer, and you can go through this at a later date. So we're going to spend an hour, and then at the end of the hour we'll open it up for questions. So you can send emails to Brian Schwartz. He's our support manager here at Vibrant, and he will read the emails. He's also on this broadcast with me, so he and I can talk back and forth. You cannot speak to me right now, but he will read your questions at the end, and then we can go back and review any and give answers to any of your questions. Let me start off by looking at this project. This is you can see that there's quite a few files in this current project. There's a structure model, which is what we're seeing animating on the screen, and we have a comparison display of 2 different shapes in the comparison. And there is a number of shape tables. So this is the data that we've saved from this particular rotor kit. And then down below are a number of macros. So these are the macro programs that we're going to look at in more detail. Last month we looked at these macro programs. I'm going to run them for you now, and we'll look at the data using the macros and hotkeys. And then we're going to go to a different project, and we'll look at macros in more detail of how they were set up with hotkeys so that we can do repetitive tasks in ME Scope. So this is programming. Once a program is set up and debugged, you can press the hotkeys, and ME Scope will just do the same thing over and over again. So we use this in a monitoring environment, or in this case we're simply going to select different cases of unbalance, and in the next project we're going to select cases of misalignment, and then we're going to compare the ODS data for a balanced machine, unbalanced, and an aligned machine, and a misaligned machine. So that's the idea here. This particular project, ME Scope project, was written up in a tech paper. Let me open it for you. And this was written back in 2009. At the IMAC conference. It was presented, International Modal Analysis Conference, and it was called Using Operating Deflection Shapes to Detect Unbalance in Rotating Equipment. Now let me just scroll through here. You can see a picture of the machine that we took the data on. This is one of the training rotor kits built by a company called Spectra Quest here in the US. But we post-process this data in ME-Scope. Now some of the terminology here, we'll clear this up in a minute when we look at another tech paper. This measure here of a shape correlation coefficient, that really is what's called the modal assurance criterion. That is a way to compare two mode shapes. And we'll go into that in a little more detail with the second paper. This SPD we don't use. We have something called a shape difference indicator now. So we do it a little differently than we did back in 2009, and I'll explain that in a minute. There's a picture of the machine, location of the inboard and outboard rotor, because we have several different cases down here, 7 different cases of unbalance. So we put a small unbalance weight on the inboard rotor, then on the outboard, then a large unbalance followed on the inboard, followed by the outboard, and then 2 large unbalances at 0 degrees apart. There we had the 2 weights so that they caused the maximum number of unbalance with the 2 rotors, and then as the machine ran, the most severe vibration. Then 2 large unbalances at 90 degrees and 2 unbalanced weights at 180. So in case number 7, the unbalances, the forces are canceling each other to some degree. You can see some data plotted here, but we're going to look at it in the project as we push hotkeys and actually look at the data in ME-Scope. This data was taken off of the running speed and the second and third order. You can see some of the peaks in here, not real clear. We do further processing on this data in ME-Scope to clear up the ODS. But basically, we're grabbing data at the peak values of, this is an auto spectrum, and then we have the phase of the cross spectrum between each of the test points and a reference test point. So that's how we get this ODS data in ME-Scope. Let me open the other paper because that's going to explain these 2 bars that you see up here on the screen. One that says MAC, Modal Assurance Criterion, the other one that says SDI. Let me pull these down here. Maybe we can see them a little better down where it's a little bit lighter. So those are the MAC and the SDI, and those are the numerical comparisons of these 2 shapes that are animating side by side. In this case, it's the same shape. So the MAC and the SDI are both indicating that the exact same shape is animating on both models. If I look over here in these shape tables, you can see that this is the baseline. And then down here it also says baseline. So we're just animating the baseline or the balanced. This is the balanced state of the machine, and the 2 shapes, of course, are the same shape. Let's go look at these calculations. This is another tech paper that we wrote, and this one was a little bit later, 2014. So it's just a year old, where we described in a tech paper the SDI calculation, the shape difference indicator. It starts off talking about MAC. Now the example here is a little different, where we're comparing modal frequencies of this Jim beam structure. But it doesn't matter, that these 2 numerical comparisons work on any 2 shapes. So here's the MAC calculation right here, the Modal Assurance Criterion. And this is a little bit of math for those of you that don't understand. Let me explain it in simple terms. I have a complex shape U, another complex shape V. Now by complex we mean that it's got magnitude and phase, or real and imaginary parts. Machinery people are used to talking magnitude and phase. That's what an ODS has in it. Mode shapes also have magnitude and phase. So this can be applied to ODS data as well as mode shape data. And another way to think of the MAC is this mathematics here is really just a dot product of the two shapes. So if you remember from high school math or maybe college where you took a dot product, you take one vector and this little h here means that I transpose it, so I turn it from a column into a row. I multiply each of its components by the components of v, in this case u multiplied by v, and that just gives me a number. Now the h is in there because these are complex. And the bottom is simply the magnitude squared, and so we're normalizing the values of the dot product by the length of each of the vectors. So that's how the answer always comes out between 0 and 1. If the shapes are the same, you can kind of see from the formula that the numerator and denominator are going to be the same, and so we get an answer of 1. If the shapes are different, the dot product is going to be a number less than 1. Here's the shape difference formula down here. Well, here's, before I go there, here's a picture of the MAC calculation between some different shapes. And you can see that the values are always between, this is a bar chart between two shape tables, and the values always go between 1 and 0. If the shapes are the same, it's 1. If they start to differ, then the values drop off to something less than 1. Now there's some other discussion here between, this is between some FEA and EMA shapes. The EMA, or the experimental shape data, maybe have different scales, in other words, different magnitudes. This is a picture showing that in fact they do have different magnitudes when we compare the EMA with the FEA shapes. We can rescale that data in Emiscope so that the scaling of the two shapes match. So that's what's going on here. But the more important thing I want to show you is down here, the shape difference indicator. This is a difference between, you can see it's similar to the MAC calculation, 1 minus, but now in the numerator is a difference between the two vectors, v and u, and then in the denominator is the sum of their magnitudes. Instead of the product, there's a sum in there. Now if I just look at, and then this, a little bit of math, it boils down into this, but if we just look at this formula and we just take some numbers, let's say that u is equal to v. So it could be a single number or a whole vector. When they're equal to each other, then the formula either up here, 2 times the real part, let's just say that they are real, we're going to get 2 times the dot product of the two divided by the sum of the two dot products. So we basically get a 1. Now it's a little clearer down here. When v and u are equal to each other, then this term here is 0. The difference is 0, and so the answer is 1. And so this has the same properties. If either v or u is 0, then the difference is 0, and here's a couple other cases here. So this again is showing a comparison. We can treat two shapes exactly the way that we treat them with the MAC calculation, except down here we see their SDI values. This is not only indicating that the shapes are the same. Remember, MAC just tells us that they are collinear. It doesn't tell us whether the magnitude of one is greater than the other. The SDI tells us whether the magnitudes are the same and the phases. So you can see in this little example, because all the values are very close to 1, it's saying that the FEA and the EMA shapes are identical in magnitude. So that's why we use both of them, and it's important in ODS when we're comparing vibration data. Let's say in this case the running speed of the machine, the first order, when we're comparing operating deflection shapes, we want to compare magnitudes as well as shapes. So let's just walk through some of these cases. Now I've got some hotkeys up here. The first one, it says balanced. So that's the case we're looking at it right now. If I push that button, Scope shows me the two shapes, and left and right are balanced. Now I'm going to push the small inboard unbalance. So now you can see that the animation has changed. On the left is the balanced, on the right is the unbalanced. You can see the machine is starting to move a little more. We took data where these accelerometer icons are. You can see where the data was taken, and then the rest is being interpolated by Scope. But over here you can see the MAC value has dropped to 82%. That's indicating that these shapes are no longer the same. But look at the SDI value. It's dropped way down to indicate that the shapes are not only different, but their magnitudes are different. And that's because the vibration level has increased for the unbalanced. Let's go to the next case here. This is the large or the small outboard. So this one was number 3, small outboard. Now you might think small outboard would cause a larger change, but in fact the MAC value is about the same for this case between the balanced and unbalanced, and the SDI typically will always be less than the MAC because it's looking at actual differences in magnitude. Let's look at the large inboard. Okay, you can see again the MAC value is saying the shape's about the same shape-wise, but vibration-wise it's quite different. The levels are greater. You can see more animation here. That's indicating that the machine is vibrating more. Here's a large outboard case. Again, MAC value didn't change a whole lot, but the SDI is dropping because it's a more severe case. All right, here's the worst case, both at 0 degrees. This is where we got 2 weights, one on each of the inboard and outboard, but at 0 degrees, so that they're, as the machine runs, those 2 weights are causing the largest unbalanced forces of all the cases. So now you can see the MAC value didn't change again. The shape is very similar. However, the SDI is dropped way down because of the magnitude difference. Here's the next case, 90 degrees. Again, this is a weight on both rotors, but they're 90 degrees apart. All right, well, 74, the MAC is not changing very much. The SDI is coming up a little bit. It's not as severe a vibration case. And then finally, we have the case of 180 degrees. So we got 2 weights on there, but they're kind of balancing each other, counterbalancing each other. Even though they're on different rotors, you can see that again, the MAC value didn't change. The shape is not that different in shape, but in magnitude it is. Now we can do that for the first order, or we can go to the second order. Sometimes if we're looking for bearing problems, we want to look at second orders. So let's go back here and start over. This is just the ODS coming off of the twice the running speed. So if we go over here, we can look at, well, we don't show the frequencies here, but basically we're running, this is data taken from the peaks at twice the running speed. In the balance case, they're the same. And if we just walk along here, I'm going to go a little more quickly. You can see now that even second order, a huge difference, MAC and SDI, even though you can't see it in the picture. Numerically, those are quite different shapes. And there they are again. Second order is a strong indicator, both MAC and SDI. Now you can see the machine start moving around a little bit. They're both indicating a quite a disparity, desperate or disparate. You can see the animation now, and SDI is virtually 0. Here's the worst case, and again, MAC is not indicating it as well as the, now remember, on the left is the balance case of the second order, and then on the right is the unbalance where the two weights are 180 degrees. So what this is showing is certainly intuitive, that as we go up in these higher frequencies, they're even more sensitive to the unbalance, the second order. Let's go to the third order. We got the third order in here, and we can kind of look. So this is kind of like modes of vibration. When you go to the higher frequencies and you upset the machine balance case, in this case, you excite different modes, and many times the high frequencies are very sensitive to any physical change. We know that if we look at structures and their stiffness or their mass changes. In this case, we have unbalanced forces. So this is really just force vibration. But as we go through these different cases, you can see that this is the third order now. Let's go over here and look at the worst case. You can see the machine is really moving around compared to the balance case at the third order. And the indicators are very strong, telling us that we have an unbalanced case. Now, let's go over and look at what we call facts. And the facts calculation uses the SDI, it uses the shape difference indicator. So now I'm in a different program, and this program is on the other side of a database, and it has the same hotkeys that I have in Emiscope. Now, the reason that they're all dimmed out is that Emiscope hasn't been hooked up to the database. So when I hook Emiscope to the database, it will archive data into the database, the shape data, and then I can compare shapes over here with facts. And facts is called the fault correlation tools. That's an acronym for fault correlation tools, and we'll take a look at that in a minute. Let's go back into Emiscope, and I'm going to set it back to the first order, and we'll set it back on the balanced case so we can recognize that. And now I'm going to go up here and connect to the database. So this is the database connection. I need something called a database connection file, a DCF file, in order to get into the database. It's a secure SQL database, so I'm going to go ahead and connect to it using this connection file, and it's connected. Now it's opened something called the machine setup. And in this machine setup, I define what I mean by a snapshot in the database. So the machine name is called Big Rotor, and I'm going to put its structure model in there. We saw that already animating. A monitored shape table is going to be the unbalanced shape data, and we're also going to use that for animation, just like Emiscope is using it. So many of the same features in Emiscope exist in the console software. Now, console can be installed on any computer. It doesn't require a license file, but it does require access to the what we call the Mechanicom database, which is the database of snapshots of data. So every time I archive data from Emiscope into the database, I can look at it then in console. So you can see how this Emiscope can be used as a monitoring tool. Post-processing, it can be acquiring data, putting it into a database, and we have customers that are already using Emiscope in this application. So over here it says in database, the machine Big Rotor is in there, and these are the data that's going to be archived by Emiscope in each snapshot. So I'm set up with the database, and over here I want to push this button right here that says Archive in Database. So that's going to start Emiscope pushing its data, and the data we're looking at here is going to go into the database. And I should be able to come over here now, and there it is. You can see that I have a baseline and a current. The same data that was just archived by Emiscope is over here animating, and this fax value is, I've already set this up so that it can identify the snapshots for each of the unbalanced cases from the database. How did I do that? We do that over here in something called events. So let me just open up the event log and we'll take a look at that. And here it is. So I have already, when a snapshot of data came in, I've already identified the unbalanced case 1 through 7. Remember, the number 1 is balanced, and then we've got the other unbalanced cases. No, number 8, I'm sorry, is the balanced case, and then 7 unbalances. And so here's the first order, second order, third order. Each of the cases have been identified from the data already in the database as a particular unbalanced case. So what fax will do, I can have thousands of snapshots of data in my database, and once I've identified a particular condition in the machine, fax will show me the top 10, based on the SDI calculation, the top 10 matching snapshots. In this case, the shape table that we logged in from Emiscope. First order, case number 1. You can see that it's put that up there. That's the first one. Now, how did I define this? Well, let's just take a quick look at how this got defined. Define the bars. I'm going to use my event storage. We've got other storage in this database called short-term and long-term. The event storage is the snapshots that I've already identified in my event log. And now if I open this up to take a look at it, here it's saying that we're going to use, here's the shape table that Emiscope logged into the database, and we're going to select all of the different components of the data. So you can see there's triaxial 0.1 and 0.2, 0.3, 0.4, and then 5 and 6Z. So these are defining the data that was taken from these accelerometers over here. And that's how I define a fax bar. So I can define a fax bar with frequencies, any shape components I like, and so forth. Now let's go up and try this out. Let's log some different data. I'm going to go here, and you can see all my hotkeys that I had in Emiscope are now available. And the last one that went in was the first order, case number 1. So let's try case number 2. So Emiscope is now, these hotkeys are being pressed in Emiscope. It's running in the background, and you can see that there's case number 2, first order. You can see that up on the top. And over here on the animated picture, you can see it's moving around a little bit more, and the SDI values are the same ones that we saw in Emiscope. So we're doing a lot of the same calculations in the console, and you can see here, Emiscope this is a little feedback here. Emiscope's telling me what it put into the database, and fax is saying, oh yeah, that's first order, case number 3. And there's the animated picture. Well, let's go to the worst case here. Let's go to this case here. both weights, number 6, both weights, and there we go. We can change this speed a little bit here. Let me go to the model and click on that, and we can change the speed of animation a little bit. And you can see the amplitude there. So very similar, really the same calculations as going on in Emiscope, but now we're pulling data from the database where we can have literally thousands of snapshots of data. And here, first order, case number 6. So FACS, using the SDI, is identifying of all the data in the database. It doesn't matter how many snapshots are in there. This is the top 10. And this unbalanced case is so severe that the numbers 2 through 10 are not even close. You can see that these are the other pieces of data that are in the database, other cases that I've put in there. So I can run this again, same way here as we ran it. Now, I've also picked a baseline. If I go to the second order, I'll have to change the baseline because I want my baseline to display. Now you can see that dropped down quite a bit. I'm going to go change my baseline to the current data that's in there. And so now you can see that my baseline and the current data are matching. Their values are both 1. And over here it's saying I'm on the second order, case number 6. Well, I didn't want case number 6, so let's go back and put case number 1 in there. That's the balance case. You can see Emiscope is doing just what I'm telling it to do here, and now it's second order case number 1. I'm going to update the baseline with that shape data. So that's my comparison just for the animated picture. FACS is still looking through all of the data, and it's saying you just passed in the current data is the second order case number 1. So now we can go back and we can try any one of these cases. Let's just try case 6 again, which is a severe unbalanced case. So there it goes. There's the animation just really moving around. And the SDI value is very small, and it's saying second order matched up with case number 6 in the database. Okay, that is all I wanted to show you from this project. Now let's go to another project, and we'll do the same thing using FACS to identify the different cases of misalignment, but I want to show you in more detail how the macro programming was done in Emiscope so that all of this automatic selection of different cases works between Emiscope and this Mechanicom database. So let's go back here, and I'm going to close this panel. So we'll close that. Now this is what we call the machine gallery. These are all the different machines that I have placed in my database. Now none of them is running right now. You can see they're all offline because Emiscope is not pushing data into the database for any of these machines. We're going to go get this machine called Spectra Quest. It's a different project. So let me go back to Emiscope and come up here. And this project here is under, remember how you do this? We put tabs for any of the folders on the disk. So I've got a tab on my tab list here of misalignment and one for unbalanced. So there's the unbalanced case that we're looking at right now. Let's go to the misalignment FACS, and I'll open up this project over here. So here's a project. Let's just do this first button here is called Start Over. So that just starts the animation, and I'll come back here and we'll explain all this to you. Now these are photo models, but it's a little cleaner. There's the photo model, not real good. It's better to show just the surface model so we can see things a little better. Let me go back here though, and let's look at the added files. So we looked at the new measure of shape difference, but let's look at this other tech paper upon which the misalignment, the use of ODS to detect misalignment was written. So this paper here was written back when. Let's get rid of this guy here. This is another IMAC conference. Okay, in 2008. So this is quite an old tech paper that we wrote talking about ODS. Now here is another description of the MAC calculation. We were calling it a shape correlation coefficient, but we've gotten away from that and we're calling it MAC, just like it really has been defined. There's the test machine. Here's a picture of the accelerometer locations. You can see we got triaxial on the two bearing blocks and on the motor. Here's some animation with the that we're going to look at here in a minute. This shows that the DOFs, when we compare the base plate ODS with the motor and bearing ODS versus all of them, that at the different first and second order, they're quite different. All right, here are the different alignment cases. We had 3 of them where the motor and the rotor are aligned properly. Here's where they're misaligned, and this is called parallel misalignment in figure B, and then in figure C is angular misalignment. So we'll see that we can use the FACS tool to identify these different misalignment cases, and we'll see it in Emiscope, the SDI calculation, as well as in the console. So here's some data here, ODS data, ODS FRF data, showing how we picked off the peaks and so forth. So let's go look at this data. And again, we're using the same 2 calculations. So here we've got a number of hotkeys. First one called aligned, second one called parallel misalignment, the third one called angular. Here are just the motor and bearings, and here are the base plate, all DOFs, and then first order, second order, archive data, and start over. So let's look at those. Where do we start here? Let's go into our macro menu and look at the hotkeys. Here's where they're defined under hotkeys setup. So make this large so we can see them. I'm going to zoom this a little bit so we can read what's in here. So here are the hotkeys I've defined in this spreadsheet. Remember, when I press a hotkey, it will execute a macro. So here are the different hotkeys. I've named them. We just went through the names. If I go up here, I can see those names, base plate. So here's one called base plate. And when I press that hotkey, it's going to execute a macro, in this case, a macro called base plate. So I've named them very similar to the function that each of the keys will do. Each of the macros will do this. Over here I can pick an icon. You can see these icons here are up here. They're the hotkeys. The first 3 are flaming hotkeys. And then I have motor and bearings and base plate and all DOFs. So I've just picked those out of a pick list here. If I open this up, you can see there's a number of keys in the list that I can pick. Let me click away here so we can. Okay, well we got those. So those are the hotkeys. The next thing that we pick to set up our macros is we can have global variables. Now we'll see how those are used in a minute, but let me just show some of them to you, because these are variables that can be shared between different macros. So I can set a variable in one macro, and then in the next macro I can read the value, and then based on the value of the global variable, I can we'll see in a minute how the logic will do different things in the various macros. So here we have a variable called which RPM. In other words, which one is this? What RPM am I looking at right now? 2,000 or 4,000? So 2,000 is the running speed, 4,000 is the second order. So it's not really running at 4,000, but we're going to look at the first order and the second order ODS. Which DOFs? Now here in the shape table, we can simply select different DOFs based on whether we're looking at the motor and bearings vibration, or the base plate vibration, or all of the DOFs, all of the accelerometers on the machine. So we can pick that, and you can see here that the variable value is actually a text that says motor and bearings, base plate, all DOFs. Which alignment? Which misalignment? So there's three cases here. The machine is aligned, it's parallel misalignment, or it's angular misalignment. And again, there's a text value for each of those variables. So I can check the variable which misalignment is it equal to parallel, angular, or aligned, and then do different things. Basically, we're just going to display different things. Archive data 0 or 1, that could be true or false. Basically, if it's a 1, it's true. If it's 0, it's false. We could actually define a true and false variable and then set the archive data to true or false. So we'll see how those all get used here in a minute. Let's go through and look at some of these macros. Okay, here's one called 2,000 RPM. So that's the first order. So what it's saying here is I want a macro that will tell Emiscope to animate the balanced versus an unbalanced case using ODSs from the first order. And I'm going to zoom out here because this spreadsheet, this is a macro spreadsheet. The above spreadsheet is a target window, so I can tell it to execute any command in an Emiscope window, and then I tell it which command to execute. That's basically it, all I have to specify. The descriptions just come when I select a command. Down in this below spreadsheet, if there are parameters associated with a particular command, then I have to put them in down here. So some of the commands, when I execute the command, I have to give it more information. Let's go up here and look at the first one. The first one says, in a shape table called baseline shape. So that's a shape table that I've created here in this project, and that's where I'm going to put the baseline or the balanced case. And then the comparison shape is going to be the misaligned case. I said that wrong. The baseline is going to be the aligned case. Let's open that up. We can just see here. Here's the aligned case at 2,000 RPM, and here's all of the ODS data from the machine, 28 degrees of freedom, and there's some numbers in there. So that's the data for the aligned. You can see the label here says aligned. So this is just some data that's sitting in here for the aligned case at the running speed. Let me put that away. So that's the first thing, and what we're going to do, we're going to select none. We're going to unselect any shapes in that shape table. Now we're going to unselect any DOFs, because if this program starts to run, if things are selected, then the animation will be based on that selection. Copy shapes from the baseline 2000 RPM, and where are we going to copy them? We're going to copy them into something called baseline shape. So the names are a little different here, but this is just copying from one shape table to another. You can see the parameter down here, destination shape table. And I want to replace what's ever in the baseline shape with data coming out of the baseline 2000 RPM. So that's a different shape table that's basically got the aligned case in it. And then I'm going to select no DOFs. So remember, the shape tables, we're going to look at motor and bearings versus a base plate versus all the DOFs by selecting DOFs. All right, we're going to go through the same type of thing here on the comparison. And now we're going to load up the comparison shape table with, first of all, we're going to unselect everything in the shape table. And here we're going to copy from the misaligned set of ODSs into something called a comparison. So the comparison is the one that's going to be displayed on the right and the baseline on the left when we do the animation. Here we're setting a variable. Which RPM? We're going to set it equal to 2000 RPM. And then we're going to start the animation. So let's look at how the animation gets started. Here's the macro program that starts the animation. Now there's a few steps in here that are not obvious, but we're going to set the rotation speed of the rotating parts of the model to match the RPM of the ODS. If we don't do that, then the model will rotate at a different speed. The rotation will not match the speed of the ODS. So if we want to look at the running speed ODS, we want to make sure the model rotates, the parts that rotate on the model, they rotate at the same speed. So that's what this is doing here. First, we're going to stop the animation. This is in the structure machine model. Draw the structure that stops the animation, or make sure that it's stopped. Now we're going to paste. Now this is a kind of a unique command here. I'm pasting into the object spreadsheet. Let's open that up and let me show you what that's doing here. This is programming. Okay, well we're animating, but up here you can see that this is column 0, this is column 1, and row 1 and 2. So what we're doing is pasting the RPM of the rotating parts. So you can see shaft and rotor is the rotating part, and it's rotating, and then there's the belts and the pulley system, and that's rotating more slowly. You can see that here, that the shaft is rotating at the speed of the machine, and then the belt is rotating, or this pulley down here is going more slowly. So the macro is setting those speeds in there based on which order I want to look at, so that I can compare the vibration at that RPM to the rotation of the machine at that RPM. So let's go back here and look at, so that's what this is doing. It's pasting, what's it pasting? It's pasting which RPM into row 1, column 1, that's the 2000. Now it's taking that variable and it's doing a little bit of arithmetic here. It's going to store, it's going to set pulley RPM equal to 0. Then it's going to, this is a little bit of a math here. It says variable 1 is equal to variable 2 operator variable 3. So I have to come down here and look at what these variables are defined as. Variable 1 is the pulley RPM, is equal to variable 2, which is which RPM, that's the 2000, divided by 4. So the pulley RPM is going to be 1/4 of the running speed, or the ODS RPM. And then that gets pasted into row 2, column 1, and the pulley RPM is going to get pasted in there, and that goes into the machine model. So that is what we're looking at here. Those two numbers are getting pasted in there. So I can edit things in various spreadsheets in Emiscope using commands like this. This is part of the macro programming so that we can manipulate data this way. All right, what else is going on here? Let me get it back. So this is, now it's coming down to another math statement. Let me make this a little smaller here so we can see what it says. It says, if variable 1 compared to variable 2, then go to step label, else go to this other step label. Well, this is called an if then else statement. So what it's saying is if the value of archived data, variable 1, is equal to the value of variable 2, which is a 1. Now remember, when archived data is equal to 1, that means archive the data into the database. So if that's true, then go to the archive. Otherwise, just go to the animate step. So here are the two steps in the program. There's one called archive, and then down here at the bottom is the one called animate. So the archive is actually going to push the data into the database so we can look at it. And it's going to do some other thing in here. You can see it's going to archive the shapes, and this is called a fact shape table. Where did that come from? Well, I'm going to take my comparison shape and copy into the facts shape table. So that's the one that's going into the database, and the machine model is going to get archived in there also. Ready the archive is an instruction from Emiscope to the database to tell it, get ready to receive some data from me, and then down here it's saying to the database, receive this data. Now here's some more messages to the database, and we saw those in the previous case. I'm going to put up messages on the message board in console. So I'm going to send to the machine called Spectra Cress. I'm going to say RPM, which RPM? So it's going to tell me which RPM is going into the database, in other words, which order. And then it's going to tell me which DOFs. Remember, the which DOFs actually said motor and bearings, base plate, or all DOFs. And then it's going to send in a message that tells which alignment case. So let's just run this here for a minute and see how this works. Now there's other macros in here. They're all quite small, and they all end up, here's the one where I want to switch back to all DOFs, so I simply first of all set a variable called which DOFs down here. You can see it's set to all DOFs. And then the baseline, we clear out the DOFs, select none, don't clear them, but unselect. Remember, animation in Emiscope will only animate selected DOFs and selected shapes. And then the comparison, the same thing, we're unselecting, and then we're going to tell it to animate the ODS. So it's going to go off and run this macro. This command here is going to run the macro, animate the ODS, and that's the one that we just looked at. So it's going to come in here and animate, here's animate ODS, and when it gets down here to checking, am I archiving or not, and it's going to say, no, I'm not archiving, come down here and start the comparison animation. So that's the command, an Emiscope command that says start the comparison animation in the machine model, and then secondly, scale the comparison shape relative to the left shape, which is the baseline shape. So that's what's going to happen. Let me push the button here and we'll just restart, and we'll walk through these various cases in Emiscope. So here we are. put that up there. So if I look over here in these shape tables, I can see what's actually animating in the two shape tables. The one above is the baseline. So that's the aligned, there's the ODS of the aligned machine when we're in alignment between the motor and the rotors. And the same thing over here, you can see down here we've got the three cases: aligned, parallel, and angular. And we're selecting the align. So I can just, since I'm animating here in Emiscope, I can just push the next button, and now I'm animating the parallel misaligned, and you can see what happened here. Well, we're not quite, there we are. This is not, let's go up here and do it. For some reason, it's not doing it right there. So there's parallel misaligned. You can see both the MAC and the SDI have dropped. So that's a strong indication of the parallel misalignment. Let's go and try the angular misalignment. Again, the MAC dropped, but the SDI dropped considerably. So that's with all the DOS. Well, let me make sure we're animating all the DOS. So we'll push the all DOS button here. Okay, so that was the all DOS case. Now let's go, let me set it back where we're comparing the aligned with the aligned. So our values are 1. And now I'm going to go and say, let's just look at motor and bearings. So let's just suppose that we only took data from the motor and the bearings. So there's the aligned case. There's the misaligned case. You can see they both went to 0. So if I simply had 3 triaxials sitting on motor and bearings on this machine and it's running in the field, both MAC and SDI would show me very strongly what has happened if I've identified that case as parallel misalignment. Let's go to the angular misalignment. Again, very strong indication, both of them dropped, so angular misalignment is occurring or is being detected by just the motor and bearings. Let's put it back to the aligned case, and now let's go and look at just the accelerometers on the base plate. So you can see that there's actually 4 of them here. There's 4 accelerometers down there on the base plate. All right, let's go to parallel misalignment. And let's go well, I'm not seeing what I expected to see. Let's go back here and see. Okay, so there they are. Now let's go to base plate. And let's look at the parallel misalignment. Okay, there's what I expected to see. The parallel misalignment is not being indicated by the accels on the base plate. Both values are very close to 1. So the base plate is not being changed by parallel misalignment. And here is the angular misalignment. Again, the MAC value hardly changed. SDI at least picked it up. And that's because the values, the numbers themselves have changed in the ODS due to the misalignment case. Okay, so we're running out of time here. We've just got a few minutes. Let's go over real quick and look at the results in the Spectra Quest machine because that data is in the database. And here we have a trend plot of some of the data and the model. And I'm going to go back to MeScope and start logging the data into the database. So I want to press this button here that says Archive Data. Let's reset everything first so we're in a known state. So here we are with all the DOS, and we're in the aligned state. And now I'm going to start the archive. All right, let's go back over to console and look at, okay, all DOS. I don't see it updating correctly here. Oh, there it is, 2000 RPM. Now this is another snapshot that was recorded as an event. So that's just saying that the snapshot that just went in is equal to the 2000 RPM aligned case. Now the reason we're not getting a match over here is perhaps the baseline has changed. So let's go back and update the baseline with the current data. There we go. So there is the balance case, and FACS is in fact identifying that case. So if I go up here and press one of the hotkeys, let's go to parallel misalignment, and parallel misalignment. So MeScope is telling us that, and there it is. You can see the values have dropped. Here's another feature in the console. I can actually look at the shape DOF values, and we haven't set up warning levels, but you can see that two of the directions are red. That means that they're in the warning condition. They've exceeded a warning level. And over here, in FACS, we're identifying parallel misalignment again. That concludes what I wanted to show. Brian, do we have any questions?
Yes, we've got a question about whether the ODS data that we're showing is using the acceleration data, or are we integrating the data to displacements?
Good question. MeScope can do integration. This is just the raw accelerometer data. So the question is, would we see the same type of change in the ODS if we were integrating the data to displacement? We could have easily put a couple lines into our macro program to do that. We can actually integrate the ODS data itself. So you can integrate right in the shape table from G's to inches or millimeters, centimeters, whatever units. MeScope will do that, and we could put that command into one of the macros where we're loading up the shape data into the appropriate shape tables, either for archiving into the database or for, but just thinking about integration of a shape, we're simply going to be dividing by the frequency of the shape. And so that's not going to change the shape. It's just going to scale the numbers down. So the shape itself should come up with the same MAC values, and the SDI values now are going to be displacement numbers, but they're all simply divided by a constant. So the shape, the numbers are not going to change in terms of whether SDI or MAC will indicate a difference. But yes, we could do that. Any other question? Machinery people typically like to look at velocity. It's kind of the happy medium between acceleration and displacement. But if we truly wanted to look at displacement, now when you look at the animated picture, you're looking at an amplified version of acceleration. So would the displacement look like this? Yes, it would. It would look very similar when we're simply displaying ODS data, because the animation will scale it so that we can look at it. And obviously I can I can change, if I go over here to the model, I can change the amplitude right here. You can see it's on an amplitude of 38. I can crank it up to whatever I want here. Oh, sorry, I'm cranking the speed. Let me crank the amplitude. So I can make the machine behave differently uh, with the animation, simply to look at the data more clearly. Okay, anything else?
No, that was the only question.
All right, well, thank you all for coming. We've spent our hour together. Next month, we will have another webinar. Not sure what we'll cover, but this pretty much clears up the use of facts for unbalance and misalignment. We'll send those tech papers to all of you that attended. We'll send the Emiscope projects. Now, you won't be able to do this facts calculation without installing the Mechanicom database and the console software. That is available, will be available on our website. Those are options to Emiscope that are extra costs, but simply extend the capability of Emiscope for monitoring, and in this case, qualification testing. If we were to bring a machine back online after maintenance, we could use facts to see that the ODS, the vibration levels, have returned to an aligned case or a balanced case that we already have in the database. All right, talk to you next month, those that are going to return for our next month's webinar.